In this video, we will explore mean absolute error, or MAE. Here is the formula for mean absolute error. In this formula, n represents the total number of data points. Y_i is the actual value for the ith observation. And y hat represents the predicted value. The mean absolute error measures the average absolute difference between the actual values and predicted values. Now, let's look at an example with some data points. Here are some example data points, showing both the actual and predicted values, along with their absolute errors. Next, we calculate the mean absolute error step by step. The calculated mean absolute error for this example is 0.525. Let's begin by visualizing the data points. The blue dots represent actual and predicted values, while the green line represents the regression line. This line illustrates the relationship between the predicted and actual values. Now, the red dashed lines highlight the absolute errors for each data point. These lines make it easier to see the deviations from the regression line. Additionally, we display the absolute error values next to each data point. Points above the regression line are labeled in green, while points below are labeled in red, providing a clear representation of the error magnitude. Let's take another example for MAE, using a fun darts analogy. Imagine you are playing darts. The bullseye in the center represents what you want to predict perfectly. Think of this as the predicted value. Now, let's throw some darts to see where they land. Each dart represents what actually happens in real life. These black darts are the actual results. Notice how they're not all on the bullseye. Some are closer, and some are farther away. To calculate MAE, we measure how far each dart is from the bullseye. These distances represent the errors. Since we don't want any negative distances, we take the absolute value of each distance. The mean absolute error is simply the average of all these distances. It tells us, on average, how far off our predictions are from the actual results. So, if the darts are closer to the bullseye, the MAE will be smaller, meaning our predictions are more accurate. MAE is like asking, how well did I play darts on average? It's simple and gives you a clear idea of prediction accuracy. Here are some key takeaways about MAE, or mean absolute error. Measures the average absolute difference between actual values and predicted values. Smaller MAE indicates better model predictions. MAE treats all errors equally, making it robust against outliers. Now, let's discuss when you should use MAE. First, MAE is particularly useful for evaluating regression models, as it provides a straightforward measure of error. Second, consider using MAE when outliers are present in the dataset. Its robust nature treats all errors equally without giving undue weight to extreme values. Lastly, MAE is ideal when you need interpretability in the same scale as the target variable. This ensures that the errors are easy to understand and communicate. On the other hand, there are cases where MAE might not be the best choice. Firstly, MAE is not suitable when penalizing larger errors more heavily is critical, as it treats all errors equally regardless of magnitude. Secondly, MAE is not applicable to classification problems or non-continuous targets, as it is designed for regression tasks. Finally, MAE can be challenging to use during training with gradient-based methods, as it has non-differentiable points that hinder optimization. By understanding when and how to use MAE, you can better evaluate regression models and make more informed decisions about your data analysis process. Thank you for watching, and see you in the next video.